Welcome to all. Today my lecture topic is kinetics of enzyme catalyst reaction. Before going to detail about this topic, some basic introduction about the topic we are going to see regarding catalyst, types of catalyst and catalysis, various types of catalysis, criteria of the catalyst. So the first term, catalyst. Catalyst is a substance is used to increase the rate of the reactions which alter the rate of the reactions without changing any amount and chemical composition of the substance. So that is called catalyst. Catalysts are mainly of two types. Number one, positive catalyst. Second one, negative catalyst. And third type is autocatalyst. Autocatalyst. So what is positive catalyst? Positive catalyst means the substance is used to increase the rate of the reaction. Is increased rate of the reactions is called positive catalyst. Example for positive catalyst, for the synthesis of ammonia in Haber process, N2 plus 3H2 in presence of iron to form ammonia, 2NH3 ammonia. Here molybdenum are also used as a catalyst. Here molybdenum acts as a positive catalyst. It is used to increase the rate of the reaction. Second one, negative catalyst. Negative catalyst means the substance is used to decrease or retard the rate of the reaction is called negative catalyst. Example for a negative catalyst, in the synthesis of decomposition of hydrogen peroxide. So decomposition of hydrogen peroxide in presence of phosphoric acid, H3PO4. H3PO4 decomposed to water and oxygen. So the H3PO4 here acted as a negative catalyst. Acted as a negative catalyst. So it is used to decrease the rate of the reaction or retard the rate of the reactions. The third type is autocatalyst. Autocatalyst means when one of the formed product acts as a catalyst is known as autocatalyst. So examples for autocatalyst reaction, for hydrolysis of ethyl acetate. Ethyl acetate CH3COO C2H5 is ethyl acetate. Hydrolysis to form acetic acid and ethanol C2H5OH. So the formed acetic acid, this formed acetic acid acts as a autocatalyst. It is used to further increase in the rate of the reactions. So the formed product acts as a catalyst means that type of substance are called autocatalyst. So these are the types of catalyst. Next, catalysis. What is mean by catalysis? So catalysis means the process of altering the rate of chemical reaction with the help of this catalyst. So the process of altering the rate of reactions with the help of the catalyst is known as catalysis. So catalysis, there are three main types of catalysis are there. Number one, homogeneous catalysis. Homogeneous catalysis. Number two, heterogeneous catalysis. Heterogeneous catalysis, homogeneous catalysis. And the third important types of catalysis is enzyme catalysis. Enzyme catalysis. So what is mean by homogeneous catalysis? We are going to see one by one. Homogeneous catalysis means the reactant and the catalyst are in same phase. The reactant or catalyst are in same phase is called homogeneous catalysis. Examples for homogeneous catalysis is oxidation of sulfur dioxide. Oxidation of sulfur dioxide with oxygen to form sulfur trioxide in presence of NO. In presence of NO. So here sulfur dioxide is a gas phase, oxygen is a gas phase, and the catalyst also a gas phase. So the homogeneous catalyst means the reactant and the catalyst are in same phase is called homogeneous. Okay, so this all are in gas phase reactions. For one more examples for liquid phase reaction is hydrolysis of ester. So hydrolysis of ester or hydrolysis of cane sugar. Cane sugar is examples for liquid phase reactions. So hydrolysis of ester, CH3, COO, C2H5 in presence of H plus acid catalyst reactions. So to form acetic acid plus ethanol. So all are in liquid form. So all are in liquid phase. So reactant and catalyst are in same phase is called as homogeneous catalysis. So the second type, heterogeneous catalysis, the reaction in which the reactant and the catalyst are in different phase means it's a heterogeneous catalysis. Reactant and catalyst are in different phase is called heterogeneous catalysis. So examples for heterogeneous catalysis is synthesis of ammonia. In Haber process, iron is act as a catalyst. Here iron is a solid phase and ammonia, nitrogen and hydrogen are a gas phase. So reactant is a gas phase and catalyst are the solid phase. So both are in different phase. So this type of reactions are called heterogeneous catalysis. In this heterogeneous catalysis, the gaseous molecule or the reactant adsorbed on the solid surface. So it's based on the contact theory. The third type of reaction is enzyme catalysis reaction. So enzyme acted as a catalyst to increase the rate of the reaction is called enzyme catalyst. So these are the classifications of catalysis. So next we are going to see the difference between homogeneous catalysis and heterogeneous catalysis. So homogeneous, heterogeneous catalysis. So what is homogeneous catalysis? We are already seen. Homogeneous catalysis means homogeneous, heterogeneous. So the first difference is reactant, catalyst, and product all are in same phase. All are in same phase is called homogeneous catalyst, whereas heterogeneous, reactant, catalyst and the products are in different phase. So different phase means heterogeneous catalyst. So this is first difference. So the second difference is catalyst are cannot regenerated. The catalyst, homogeneous catalyst cannot regenerated because all are in same phase. Its regeneration is very difficult. Here catalyst is a solid one, so regeneration is easy. So the catalyst are can be regenerated. So third difference is thermal stability of the homogeneous catalyst is low. Thermal stability is low. Whereas heterogeneous catalyst, thermal stability is high. Thermal stability is high. The reaction is carried out in a homogeneous catalyst reactions at low temperature and pressure. Low temperature and pressure. The homogeneous catalyst reactions is carried out at low temperature and pressure, whereas heterogeneous catalyst reactions is carried out at high temperature and pressure. So in the homogeneous reactions, the reaction is does not depend on the physical nature of the catalyst. Here it depends on the physical nature of the catalyst. So these are the some difference between homogeneous catalyst and heterogeneous catalyst. Next we move on to criteria of the catalyst. Catalyst having some general characteristics. So we are going to see the characteristics of catalyst. Or criteria of the catalysis. So the first point, the first basic characteristics of the catalyst does not change the amount and chemical composition of the catalyst amount. It does not change the chemical composition at the end of the reactions. So that is first point. So does not change the weight as well as chemical composition of the catalyst till at the end of the reactions, whereas the only color change or physical nature slightly changes. So the second point, catalysts are more efficient. Catalysts are more efficient than normal without catalyst reactions. So third point, catalysts are more specific in nature. So each catalyst work within the reaction. So catalysts are specific in nature. So it is more efficient. Catalysts are specific in nature. So catalyst does not change. Amount and chemical composition. At the end of the reactions. So fourth point, it is catalysts are highly active when the catalysts are in finely divided particles. So if it is in the solid form, it's a lower the rate of the reactions. If you are using the finely divided solid particles, the catalytic activity is more. The catalyst is poisoned by adding some other substance. So it can be poisoned by other substances. Sixth point, the catalyst does not alter the equilibrium position of the reactions. It does not alter the equilibrium position of the reversible reaction. So for example, decomposition of hydrogen iodide. Decomposition of hydrogen iodide is in a reversible reaction. So it gets decomposed into hydrogen and iodine. So we are using catalyst. It does not alter the concentration of the reactant or the concentration of the product. So it does not interfere the position of the equilibrium. So likewise, the catalyst does not initiate the reactions. So whether we are using catalyst or without using catalyst, the reaction is going on. If you are without using catalyst, the reaction is slower, whereas if you are using catalyst, the reaction is faster. So the reaction does not initiate the reaction. So the reaction catalyst does not initiate the reactions, which is only used to increase the rate of the reaction. So these are the points, basic criteria of the catalyst. So next we move on to our topic, enzyme catalysis. So enzyme catalysis Enzyme catalysis. Enzyme catalysis means the enzyme acted as a catalyst is used to alter the rate of the reaction is called enzyme catalyst. The catalysis reaction is brought about by enzyme is called enzyme catalysis reactions. So, what is enzyme? Enzymes are high molecular weight protein molecules. So, high molecular weight protein molecules are called enzymes. So, these enzymes are acted as a catalyst is called enzyme catalyst reactions. So, there are some examples of enzyme catalyst reactions. So, first one, the enzyme diastase. Enzyme diastase is used to convert starch into maltose. Starch into maltose. Starch into maltose. So, the enzyme diastase is used to convert starch into maltose. So, the molecular formula of starch is C6H10O5 N time. So, N time starch, here is the N. So, starch hydrolysis N time H2O in presence of diastase to form maltose. Maltose is a disaccharide. So, molecular formula of maltose is C12H22O11. This is molecular formula of maltose. So, enzyme diastase is used to convert the starch into maltose. So, this is one example. The second example is maltase. Maltase, the enzyme maltase is used to convert the maltose into glucose. Maltose into glucose. So, molecular formula of maltose is C12H22O11 hydrolysis in presence of maltase to form glucose C6H12O6. It is a monosaccharide. So, to form glucose. The third examples for enzyme catalyst reactions are enzyme cymase. Enzyme cymase used to convert glucose into ethyl alcohol, that means ethanol. Ethyl alcohol. So, glucose molecular formula C6H12O6 in the enzyme zymase. So, it's degrade the glucose into ethanol C2H5OH, ethanol plus CO2. So, the enzyme zymase is used to degradation of glucose into ethyl alcohol. The fourth enzyme catalyst reactions are invertase. The enzyme invertase is used to sucrose into glucose and fructose. So, sucrose is a disaccharide C12H22O11. So, its hydrolysis in the presence of enzyme invertase to form glucose and fructose C6H12O11 glucose plus C6H12O11 fructose. So, this reactions is otherwise called inversion of cane sugar. So, fifth example of enzyme catalyst reactions are the enzyme urease used to hydrolyze the urea diamide NH2C double bond O NH2. It is a molecular formula of urea. So, urea it is hydrolyzed in presence of urease to form ammonia and carbon dioxide. So 2 molecules of ammonia. So urea hydrolysis, in presence of ureases, it give ammonia and carbon dioxide. So all these enzyme ends with ASE, A-S-E, ASE. So enzyme, all enzyme name end with ASE. Diastase, maltase, zymase, invertase and urases. So all these kinds of enzymes are acted as a catalyst to increase the rate of the reaction. So these are the some of the examples of enzyme catalyst reactions. So next we are moving to mechanism of enzyme catalyst reaction. So before that, criteria of enzyme catalyst reactions are going to explain. So characteristics of enzyme or criteria of enzyme catalyst reactions. So criteria of enzyme catalyst reaction. Criteria of enzyme catalyst reactions. Here first point, enzyme catalyst reactions are more efficient than other catalysts. So first point, it is more efficient. Enzyme catalyst reactions are more efficient. Second point, enzyme catalyst reactions are specific in nature. Specific in nature. So third one, enzyme catalyst reactions, the rate of enzyme catalyst reactions is very high at maximum temperature or very high at optimum temperature. Optimum temperature. So fourth one, the rate of enzyme catalyst reactions is very high at optimum pH. Optimum pH. So the enzyme catalyst reactions are activated by promoter or coenzyme. Enzyme catalyst reactions are activated by promoters or coenzymes. Sixth point, the enzyme catalyst reactions are poisoned by inhibitor. Poisoned by inhibitor. So these are some main criteria of enzyme catalyst reaction. So the first point we are going to see in detail, more efficient. Enzyme catalysts are more efficient than other using the other type of catalyst like inorganic catalyst. So example, hydrogen peroxide decomposition. Hydrogen peroxide decomposition, it will give H2O plus oxygen. So this catalyst rate without catalyst, EA value, energy of activation. So this is reactions. Energy of activation is very high for without catalyst. Without catalyst, EA value, energy of activation values is very high without catalyst. Where if it is using with catalyst, that means colloidal platinum as a catalyst, they are using, the EA value is little decreases. If you are using enzyme catalyst, the EA value is very less than compared to other catalyst. So with use of enzyme catalyst, here with use of colloidal platinum acted as a catalyst. So EA value decreases means the rate of reaction is more because the reaction pathway is very less. So it speed up the reaction. So rate of the reaction is greater when you are using enzyme catalyst. EA versus rate. So without catalyst, the EA value is 18 kilocalorie per mole. When you are using the reaction decomposition of hydrogen peroxide without catalyst, the EA value of that reaction is 18 kilocalorie per mole. Whereas we are using colloidal platinum acted as a catalyst, the EA value is 11 kilocalorie per mole. So little decreases, the EA value is little decreases, that means the speed of the reaction is slight increases. Whereas using enzyme catalyst, the EA value is less than 2 kilocalorie per mole. That means EA value is highly decreases, so rate of the reaction is increases more. So when you are using enzyme catalyst is more efficient than other catalyst. The second one, enzyme catalyst reactions are specific in nature. That means one enzyme used in a particular reaction, it does not work on the other type of reaction. That is called specific in nature. So for example, enzyme urease hydrolyzes the only urea. Molecular formula of urea NH2C double bond O NH2. So it hydrolyzes by urease to give ammonia and carbon dioxide, whereas the same urases does not hydrolyze the other amide, like means methylamide NH2 C double bond O NHCH3. Instead of hydrogen, we are substituting one methyl group. It's methylamide. It does not, in the presence of urase, it does not hydrolyze this methylamide. That means each enzyme have specific in nature. It's particularly worked on that reactions only. So here there is no reaction. So enzymes are specific in nature. Third one, optimum temperature. The rate of enzyme catalyst reactions is maximum at optimum temperature. That means at a particular temperature, the rate of the reaction is very high. It indicates the optimum temperature. That is called optimum temperature. The rate at which the reaction is maximum is called optimum temperature. Example, our body temperature is 37 degrees Celsius. So our blood, our pH, our temperature of the body temperature is 37. So all the enzyme catalyst reactions in our body carried out at this temperature level. If you are increasing the temperature during fever time, we are suffering a lot. So optimum temperature is, enzyme is 37, that is called optimum temperature. Next, optimum pH. The enzyme catalyst reactions are very high at the particular pH. If a pH value changes, either it is low or higher, the enzymes are denatured. That means maximum enzyme are active in a neutral range, in a neutral pH range. So, example, our body flood pH is 7.4 as well as body fluid, the pH range is 7.4. So, if it is pH values are decreases or increases, the optimum, the enzymes are denatured, it does not act as a catalyst. So, the pH at a particular pH, the rate of the reaction is very more, that pH is called optimum pH. So, optimum pH of enzyme in our body is neutral pH 7.4. The next one, enzyme catalyst reactions are activated by using promoter or coenzymes. That means if any substance added to the reactions which is used to increase the rate of the reaction, that substance are called promoter or coenzyme. Coenzyme means non-protein part. Enzymes are protein part, coenzymes are non-protein part. So if you are adding some of non-protein part into the reaction, it's used to increase the rate of the reaction, that is called coenzymes. So examples for promoters: so inhibitor means if you are adding the substance which it is used to decrease or inhibit the rate of the reaction, that is called inhibitors. So examples for inhibitors: enzyme enzyme having thiol group, SH group, if you are adding silver, enzyme S silver, it remove the H plus. So it will arrest the thiol group, the reaction get poisoned and the rate of the reaction is decreases. So this enzyme catalyst reaction is poisoned by in presence of silver. So silver acted as a inhibitor or poisoner. For activator, ammonia synthesis N2 plus H2 to H2 to form ammonia. Here acted as a acted as a catalyst. So this one is acted as a promoter or positive catalyst. Okay, so these are the basic important criteria of enzyme catalyst reactions. So first one is enzyme catalyst reactions are more efficient, it is more specific in nature, the rate of reaction is maximum at optimum temperature and the rate of the reaction is maximum at optimum pH, and the rate of reaction is activated by using promoter or coenzymes, the rate of reaction is inhibited by adding inhibitor. So these are basic characteristics of enzyme catalyst reactions. So next we want to kinetics of mechanism of enzyme catalyst reactions. So the mechanism of enzyme catalyst reactions are proposed by two biochemists. The name is Michalies and L. Michalies and M. Menten in 1913 proposed a kinetics of mechanism of enzyme catalyst reactions. So the enzyme catalyst reactions follows the following steps. It follows the following steps. Let us consider enzyme react with the substrate to form the intermediate complex X. So enzyme E react with the substrate to form the intermediate complex X. So this is considered as equation number 1. This part is very, very important. So enzyme E is a enzyme, S is a substrate, K1. So it gives intermediate complex X. Intermediate complex X. So this is equation number 1. Here there are two possibilities. The intermediate complex X may decompose back into enzyme and substrate, or it may form the product. So there are two possibilities. So the first one, the intermediate complex decomposes back to form enzyme and substrate. So equation number 2 can be written as X in presence of K in K2 to form E plus S. So this is equation number 2. The third, intermediate complex may form the product means X converted to product P. So this is equation number 3. Here K1, K2 and K3 are called rate constants. Rate constants for a particular reactions respectively. Particular reactions respectively. So K1, the first reaction is the fastest reactions. So K1, K2, K3 are the rate constants for a particular reactions. Here, a rate of reactions we are going to write. So before that, you are known how to write the rate of the reactions. If you are writing the concentration of substrate with respect to time, concentration of product with respect to time. So we plot the graph, concentration of substrate with respect to time and concentration of product with respect to time. So concentration of when you increase the time, the concentration of the substance is decreases. Concentration of substrate is decreases when increasing the time, whereas concentration of product is increases when increasing in the time. So here we can write the rate equation, rate equal to minus ds by dt, because with respect to time, the rate of the reaction, concentration of the substrate is decreases. So concentration of the reacting substrate is decreases when the time is increases. So rate of the reaction we can return in the form of minus, whereas the rate of concentration of product, the concentration of product is increases with respect to time. So we can write in the positive form. So rate equal to dp by dt. So rate of the reaction writing in the product side, we can use positive sign. Rate of the reaction writing in a negative side, we can use negative sign. So substrate minus ds by dt, whereas product dp by dt positive. So from the slope of the reaction, we can get the information about the kinetics reactions. So we are going to write the rate equation for the formation of intermediate complex. So for the formation of intermediate complex, x can be written as dx by dt equal to, so here x is a positive side, so K1 concentration of enzyme and concentration of substrate, minus, it's a negative substrate side, so K2 x, this x also is substrate side, so minus K3x. So this is equation number 4. So this equation may be written as K1 E S minus x getting constant, so it will take outside K2 plus K3. So this is equation number 4. So equation number 4, the rate of intermediate complex can be written as, from this rate constant equation, we get equation number 4. The rate of formation of product dp by dt equal to the product K3x. So K3x. So all we can write in the square bracket, that means concentration of enzyme, this is concentration of substrate, this is concentration of intermediate complex. So all the things can be written in a square bracket that indicates molar concentration of the particular species. So rate of concentration of product can be written as dp by dt equal to K3x. So this is equation number 5. As we know that total enzyme concentration E0 is equal to the enzyme present in the unreactant form and enzyme present in the intermediate complex. So the total enzyme E0 equal to enzyme present in the unreacted form plus enzyme present in the intermediate complex X. So E is the enzyme present in unreacted form. This is enzyme present in the intermediate complex. So E0 is a total enzyme concentration. So we can write this one, E equal to E0 minus X. E0 minus X. So we can substitute this E0 minus X, E value in this equation number 4. So substitute the E value in equation number 4. So K1 E0 minus X into X minus X into K2 plus K3. K2 plus K3. So equation number 4, we can substitute instead of E, we can substitute E minus X. So this is equation number 6. Equation number here, E0 is the total concentration of the enzyme, X is the enzyme present in the intermediate complex, S is concentration of substrate. So the rate of formation of intermediate complex is unstable, so it decomposes instantaneously. So dx by dt equal to 0 because it is unstable. So there is no intermediate complex, means that is 0. This is equation number 7. So at this stage, the equation 6 can be written as K1E0x into S minus X into equal to, because this one is 0. So we are writing this equal X into K2 plus K3. This is equation number 8. And next, we multiply this S on these two terms. We can write K1E0S minus K1 X into S equal to X into K2 plus K3. This is equation number 9. So again, the negative term changed to equal to that side. So E0 S equal to K1X S plus X into K2 plus K3. This is equation number 10. Again, the X getting common. So we can change K1S, K2 plus K3, X is the common term. So we are taking outside this X and this X, it's a common outside. So we are getting equation number 11. So from that, we can write the X. So X equal to K1 E0S divided by, come into denominator, K1S plus K2 plus K3. So this is equation number 12. So from this equation, we are getting X value. So this X value, this equation, we are divided K1S divided by K1S for both the denominator and numerator. We can get the equation number 13. So X equal to K1 E0 S by divided by K1S divided by K1S plus K2 plus K3 by K1S. So both numerator and denominator divided by K1S. So we are getting X equal to E0 divided by 1 plus, this one cancel, 1 plus K2 plus K3 by K1S. So this is equation number 13. Equation number 13. We can substitute this equation number 13 X value in equation number 5. So this X value we can substitute in equation number 5. So dP by dt equal to K3, instead of X we can substitute E0 by 1 plus K2 plus K3 by K1S. So here multiply this equation by S. So multiply by S. So this is equation number 14 and multiplied by S. So K3 E0S divided by, all we have to write in a square bracket, S plus K2 plus K3 by K1S. So here K2 plus K3 divided by K1 is called it as common constant Km. So Km is known as Michaelis constant, Michaelis Menten constant. So instead of K2 plus K3 by K1, we can substitute Km value. So the rate dP by dt equal to K3 E0S divided by Km by S, 1 plus Km plus S. So this is equation number 15. Now, so not here multiplied by S, we are going to multiply by S for this step only. So equation 15, multiply the substrate, we can get the equation number 16, K3 E0 S divided by S plus Km by S. So this is equation number 16. So Km, this is equation number 16, is known as Michaelis Menten equation. Michaelis Menten equation. So equation 16 is known as Michaelis Menten equation, K3 E0S divided by S plus Km. So dP by dt equal to K3 E0S divided by S plus Km. So Km is a Michaelis Menten constant. This equation is known as Michaelis Menten equation. So here there are two important cases we are applied. The first case is at lower concentration of the substrate. The first case is, from that equation we can apply the two cases. Case 1, at lower concentration of the substrate. So at lower concentration of the substrate, the rate of reaction is increases initially at lower concentration of the substrate. So equation 16 can be written as substrate concentration is lesser than Km value. So at lower concentration of the substrate concentration is very less compared to Km value. So the equation 16, the denominator S can be neglected because S concentration is very less, it can be neglected. So equation 16 can be written as dP by dt equal to K3 E0 substrate divided by, in denominator S is neglected, so Km only. So this is equation number 17. Here the rate of the reaction is first order with respect to substrate. So rate of the reaction is first order with respect to substrate concentration. Where in the case 2, at high concentration of the substrate, so the condition is substrate concentration is greater than Km value. So in the denominator Km can be neglected. So equation 16 can be written as dP by dt equal to K3 E0 S divided by S. So Km can be neglected. So S getting cancelled. So the reaction is K3 E0. So the rate of the reaction does not depends on the substrate, it's only total enzyme. So this is zero order reaction. Because the concentration of the substrate, it does not increase the rate of the reactions, it does not depends on the substrate, so it is zero order reactions. So these two conditions are explained by the rate of effect of substrate on rate. So the next topic is effect of substrate on rate. So the above two cases are explained by effect of substrate on rate. So the enzyme catalyst reactions, the rate of reaction increases from first order to zero order. This is due to presence of one or more active site present in the enzyme molecule. So this can be explained. The first one, at lower concentration of the substrate, the active sites of the enzymes remains unoccupied at any stage. The cavities, the active sites are free. So we are adding substrate concentration, it's occupy the active sites and increase the rate of the reaction. So it's the condition. So the active site are vacant, so it's unoccupied. If we are adding substrate concentration, it's sitting on the vacant place and used to increase the rate of the reaction. That is the reason. So the second one, at high concentration of the substrate, already the vacant sites are occupied at any stage. There is no free space to occupy for the active site. So the further increasing the concentration of substrate, there is no change in the rate of the reactions. So at higher concentration of substrate, the reaction rate is zero order. Here follows first order. So this can be explained in the graphical way. So concentration of substrate, rate versus substrate. At lower concentration of substrate, the rate of the graph will obtained like this. At lower concentration of substrate, the rate of reaction is getting linear form. That indicates the rate of the reaction is first order with respect to substrate concentration. When further increasing the concentration of the substrate, the rate of the reaction is, there is no change. It's obtained the plateau region. There is no change in the rate of the reactions. That means it's indicate the zero order reaction. The rate at maximum is called Vmax. The concentration at a particular concentration of the substrate, the rate is maximum, that is called Vmax. So the rate is first order with respect to lower concentration of the substrate, zero order with respect to higher concentration of the substrate. So next, importance of Michalies Menten equation. The Km also going to calculate. So the Michalies Menten equation, So all the enzymes are converted into product. There is no free enzyme. That means the total enzyme, previously we can write total enzyme equal to E plus X. Previously we can write like this, total enzyme equal to enzyme, unreacted enzyme plus enzyme in the intermediate complex. So Michalies Menten equation, all the enzymes are utilized, there is no free enzyme. So we can neglect the E value. So E0 equal to X. So we can substitute this in equation number 6, product equation. So dP by dt, K3, instead of X we can substitute E0 value. So this is K3E0 is called rate at maximum, it's called Vmax. So Vmax is nothing but maximum rate. Vmax is called as maximum rate. So instead of K3x, we can substitute Vmax in equation number 16, that is Michalies Menten equation. So dP by dt equal to K3E0 S by S plus Km. This is Michalies Menten equation. Here instead of K3E0, we can substitute Vmax. So Vmax into substrate divided by plus Km. So this is equation number 17. I think so. Equation number 19. So this is Vmax substrate by S plus Km. In this condition, if suppose Km concentration is equal to substrate concentration, means the Km concentration, Michalies Menten concentration is equal to the concentration of substrate, means the equation can be written as Vmax substrate divided by substrate plus substrate. So we can get Vmax into substrate divided by 2s. So s getting cancelled. So we can get Vmax by 2. So equation number 20. So rate of reaction dP by dt equal to Vmax by 2. If Vmax, that means Vmax equal to K3E0. We can substitute K3E0 Vmax, we can get Vmax by half. That means the rate of Michalies Menten constant is equal to the concentration of the substrate. It is equal to the maximum rate, half of the maximum rate of the reaction at a higher concentration of the substrate. So Km can be defined as Km is equal to the concentration of the substrate. The rate of formation of product is the half of the maximum rate of the reaction at higher concentration of the substrate. So Km can be explained from these equations. So next we are going to calculate the Km value from the graphical value. So we can get the linear equations as well as the zero order reactions explained by Michalies Menten equation. First order, zero order, both can be explained by Michalies Menten equations. So from the first order linear equation, we are going to calculate the Km value. So this equation 19 can be write in the reciprocal form. So calculation of Km value from the reciprocal equation from the 19. So the reciprocal of Michalies Menten equation, is called Line-Weber-Burke equation. Line-Weber-Burke equation. So the reciprocal of Michalies Menten equation is known as Line-Weber-Burke equation. So from this equation, we can write the reciprocal equation. So 1 by rate, this is rate. So 1 by rate equal to 1 by Vmax plus Km by Vmax into substrate. So this is equation number 21. So this equation is called Line-Weber-Burke equation. So this equation looks like a linear equation, y equal to mx plus c. So we can draw the graph between 1 by rate versus 1 by substrate. So we are draw a graph like this, 1 by rate versus 1 by substrate. We can get a straight line with the intercept of 1 by V max, intercept equal to 1 by V max. So slope equal Km by V max. So from the slope, the Km value can be calculated. So Km equal to slope into V max. So from this graphical value, the Km, Michalies Menten constant, can be calculated. I hope you are understand the kinetics of enzyme catalyst reactions. From that equations we can get the Km value, Michalies Menten constants. So next we are going to see the factors affecting enzyme catalyst reactions. Factors affecting enzyme catalyst reaction. So enzyme catalyst reactions depends on the substrate, that's already we know. At lower concentration of the substrate, the rate is increases. At higher concentration of the substrate, the rate is, it's a zero order, it's independent of substrate. That is first point. And the second one, the pH is, enzyme catalyst reactions depends on the pH. The second one, enzyme catalyst reactions depends on the temperature, and enzyme catalyst reactions is depends on the promoter or inhibitors. The fourth one, it depends on the salt concentration. So the rate of enzyme catalyst reactions depends on the pH. So yeah, all the enzymes are active at a neutral pH. It is deviate from lower or higher side, the enzymes are denatured and the catalytic activity are decreases. If you are using lower concentration, if you are increasing the concentration of temperature, the rate of the reaction is increases at a particular temperature, whereas further increasing the temperature, there is no change in the rate of the reaction. That means the temperature at a particular temperature, the rate is maximum, that is optimum temperature. Beyond the temperature, the enzymes get denatured, there is no change in the reaction rate. Next, the enzyme catalyst reactions is highly enhanced by adding promoter, or it can be poisoned or retard the rate of the reaction by adding inhibitor. So these are involved or interfere the enzyme catalyst reactions. Next, salt concentration. Salt concentration of the depends on the enzyme catalyst reactions. So lower concentration of the salt, at lower concentration of the salt, the charged amino acid particles are close to each other. They are getting connected. So the enzyme catalyst reactions are faster, whereas at higher concentration of salt, there is no blocking the possibilities of interconnecting the charged amino acid particles, so it can get precipitated, the enzymes get precipitated. So the salt concentration also depends on the enzyme catalyst reaction. So these are the factors affecting enzyme catalyst reactions. Next, applications of enzyme catalyst reactions. Enzyme catalyst reactions are used in various biological reactions like digestion, protein synthesis, DNA replication, etc. So there are various biochemical process, the enzyme catalyst reactions are used. It is a very fundamental reactions in our human body, so enzyme catalyst reactions are very important. Also it is used, enzyme catalyst reactions in used in medical, for wound healing or other purposes. It is used in pharma. So the first applications is used in biological process. Second application, it is used in pharmaceutical, for making drugs industries, wound healing, enzyme catalyst reactions are used. Various industries, so enzyme catalyst used in various industries like textile, food and flavor, food and breweries, biofuel industries. So there are various industries the enzyme catalyst reactions are used. The biotechnological process, the research areas, the enzyme catalyst reactions are concentrate more. So there are various fields the enzyme catalyst reactions are used. Next, advantages of enzyme catalyst reaction. Advantages of enzyme catalyst reactions, it is very uh, important advantages. Enzyme catalyst reactions are, the reaction condition is very low. Reaction conditions, so condition is very important. So enzyme catalyst reactions is, it's used as a moderate conditions, so no need of any different difficult conditions. So the condition is mild. Enzyme catalyst reactions are highly efficient, and convenient method. So it is very specific, efficient, convenient methods. And enzyme catalyst reactions is very important point. It's a eco-friendly method. Eco-friendly, that is all enzymes are biodegradable. Biodegradable catalyst. So it is a very eco-friendly catalyst for using catalysis industries. So these are the advantages while using enzyme catalyst reactions. So our today classes, catalysis, types of catalysis, basic criteria of the catalysis, various types of catalyst reactions, that is homogeneous reaction, heterogeneous reactions, and enzyme catalyst reactions. After that, the enzyme catalyst reactions definition, some examples of enzyme catalyst reactions, and basic characteristics of enzyme characteristic reactions are seen. Uh, the detailed kinetic and mechanism of enzyme catalyst reactions are derived here. That is Michalies and Menten proposed that theory. So from that, Km value can be calculated. Km value calculated from the graph 1 by rate versus substrate. Rate versus substrate, we are getting straight line. From the intercept and slope value, Km can be calculated. I hope you are understand. So today I finished my lecture. Thank you for watching. Sir, finish my